So hi everyone. Today we are doing the lecture over Zoom because there is some SATs exam happening at the university, and we are at lecture 7. So just to kind of show you where we are and what we are going to do today. So today we are essentially going to talk about pseudorandom generators in the first part. In particular, we are going to cover Fourier analysis, which will allow us to use epsilon bias sets in this context of pseudorandom generators. And then we are going to talk about what's usually called k-wise independence. The proper name is probably bounded independence. So that's probably all we'll do today. Next week, we are going to continue with pseudorandom generators. And maybe also a little bit, we'll steal some time from lecture 9. And then in the remaining 2.5 lectures, we are going to switch topics and talk about randomness extractors. Now, some good news are that Itai Cohen, our TA, is here. I don't know if it's actually here right now at Zoom, but he's at the university. And so he'll give his recitations from here on. And today we will talk about expander codes. So it has nothing to do with small bias sets or pseudorandom generators. It's something related to lecture, like end of lecture 6 and previously. So as I told you, like there are two ways to construct codes, either using polynomials or polynomial-like functions, or using expanders. There really are only two kinds of codes, even though it's a big field. And these are two topics we learned, so we are going to see the second type of codes today, which is really cool. And next week, Itai is going to talk about a really kind of important result, which is pseudorandom generators for low-degree polynomials. So epsilon bias sets, when I will start this lecture today, I will say that this is a pseudorandom generator for linear tests, namely linear degree 1 polynomials. And Itai will show how to use epsilon bias sets to obtain a PRG for a larger class of functions, much more complicated class of functions. Okay, any questions about where we are and where we are going and so forth? Or anything? Okay, so let's just dive right into the definition of a pseudorandom generator. Okay, so let me just first give the kind of dry definition and then I can philosophize about it. So say you have a class of function, and our functions are just going to be Boolean functions, like from the Boolean cube to 0, 1. So C is some class of functions, some subset of these functions, which you are interested in. So pseudorandom generator, it's a long word, pseudo, or 2 words, random generator for C, for this class, with error epsilon is a function. So it's a function that will denote by PRG, abbreviating pseudorandom generator. It's going to take as input a bit string, but with this new parameter R, and it's going to output an input for a function in the class. So it's going to output an n-bit string. But it's not just some function, such that, and now I'm just going to write something that kind of try to capture the fact that the output of the pseudorandom generator looks uniform to this class. So for every function in the class, if you'll feed to this function the output of a pseudorandom generator, or you feed to the generator, are independent and uniform bits. So UR stands for the uniform distribution over R bits. Right, so that's uniform distribution over 0, 1 to the R. So if you do that, and you will compare it against what would happen if you would actually just feed to that function from the class the uniform distribution over n bits. When you want these two values, these are numbered between 0 and 1, because the function is Boolean. When you want, well, I should take the expectation, I guess. When you want the difference between the expectations to be at most epsilon. Okay, so let's see. So you're given a class of functions, and we define a pseudorandom generator for this class. It's too dark. For this class, with some parameter arrow epsilon, to be this kind of magical function that when you take any function from the class and you apply f to every output of the PRG, right? A uniform output of the PRG, in other words, you feed in a uniform input and see what you get, the n bits that you get, and feed that to f, and you take the expectation of that compared to the actual expectation of the function, like with respect to the uniform distribution. You want this to be at most epsilon. You want these inputs to look uniform to this function and to any function in C. So this notion of a pseudorandom generator is kind of tries to, it has applications, but the philosophical aspect of it is that it tries to say something in the form that, randomness is in the eye of the beholder. So this random variable, especially if R is very small compared to N, is certainly not going to be uniform, right? Because you're using just R random bits, and you output n bits. So so what you're really doing is you're outputting 2 R strings from 0, 1 to the n, and that could be much smaller than the entire set of 0, 1 to the n. So this small set, which is not random, like information theoretically, it's not random. It's not uniform over n bits. It's not random, not sufficiently random. It looks random to f, because f cannot distinguish it better than with probability epsilon from the uniform distribution. Right? That's what taking the expectation actually means. Another way to view it is saying, like, instead of looking at the expectation, right, the expectation of a variable which is 0, 1 is really just the probability of the variable to be 1. Right? That's the expectation in this particular case. So you can think of f as f has its own life and it does stuff, but in this context, you can think of f as trying to distinguish between the output distribution of this function, PRG, and uniform. The only thing, it's kind of a paranoid function. The only thing it tries to do, it doesn't try to solve any problem. The only thing it tries to do is to figure out whether you lie to it and fed it with this kind of pseudo-random input, a random input which is not truly uniform over n bits. So you can think of f as outputting 1 if it thinks that the output came from the PRG, and 0 if it thinks it came from the uniform distribution. And you can essentially, but just by playing with the relation with the expectation and the 0, 1 function, what really happening is that this function cannot distinguish, in that sense, an input coming from this pseudo-random distribution and an input coming from truly random n bits, truly n random bits. Right? So that's the notion of a PRG. And I should just say that we sometimes use phrases like PRG, like this function, epsilon fools f or c, like if you consider the entire class fools the class, or if you have a particular function in mind when you fools this function. And we also abbreviate. We are never going to write this again. We are just going to say that instead of saying a pseudo-random generator for C with arrow epsilon, we are just going to say that this function is an epsilon PRG. Epsilon PRG is a epsilon pseudo-random generator, arrow epsilon pseudo-random generator. Okay, which is a bit confusing because that's also the function name usually. But yeah, okay, it's never a problem. Any questions about this definition?
Is it considered sometimes for non Boolean functions. So when the target is 0, 1 to the something.
Yes, good, very good. Yeah, so I'm kind of somewhat simplifying here and only assuming that, first of all, the input is over the Boolean cube and the output is 0, 1. There are like two things I kind of assumed here. And you don't have to assume that. And actually, we will consider generalization later on, but I wanted to start with the kind of cleanest definition as possible. I don't know if cleanest, but less. It's certainly the most useful one in this context of complexity, and but it's also the kind of, in a sense, the simplest one. But we will definitely care about outputs being not just 0, 1, and like today also, and inputs not just the Boolean cube. This kind of corresponds to functions, actually to kind of languages in complexity, right? You either accept or reject an n-bit string, but you may have like a computational problem where you add numbers or whatever, and this range is actually R or N or whatever, or maybe it's a group for some reason. There are reasons. And the input actually may also be larger. Maybe not R to the N, because then it's hard to find a small set that looks like R to the N, but yes, that's a great question, and yes, definitely. That's a particular case of a pseudo-random generator. More questions? We will see like several pseudo-random generators today, so it will be clearer, but still, any other question? Okay, so in fact, we already saw one, and I told you that last time, in the last hour of last lecture, we saw a pseudo-random generator for some class, and we called it an epsilon bias set without putting it in the context of a pseudo-random generator. So let me remind you the definition of an epsilon bias set. So yeah, I don't know, I really want it to be still here. Okay, let's do this thing, just so you'll have it in front of you. That's kind of the magic of Zoom talks. Okay, so it's here. Okay, so just as a reminder, right? So a set S in 0, 1 to the n is an epsilon biased set if, and then I wrote this weird condition for any tau, I called it, so for any kind of non-zero vector. Yeah, so I don't want to be too formal here, but yeah, like that. For any non-zero vector, if you take the expectation right, so for any non-zero vector, if you sample S from S, when I write it like that, I mean that I'm sampling S from S. That's a kind of a capital S sitting here. So if I'm sampling S for S and ask, what's the inner product, either in 0, 1 or in the integers, it doesn't really matter because of this -1 here. What's the inner product between this linear function, linear tests, and this sample? When I want that to be I want that to be kind of unbiased. I want essentially half of them plus minus epsilon to be 1 and half of them to be 0. Right? And this -1 is just kind of a gadget for translating 0 here to -1 to 1 and 1 here to -1, so that they will kind of instead of writing I want to be close to half, I can write I want it to be small, because the number of ones and -1s should be roughly the same. Right, so that was an epsilon bias set, and we actually constructed epsilon bias sets of that size. I never know how to put it like that. And I told you that you can do better. And we did something else a little bit also with the Hermitian curve, but never mind that now. And so do you see why this is also a pseudo-random generator? I mean, there are some things that look similar. I mean, there is no function, there is a set. So that's a difference. And but it's just cosmetic difference. And there are absolute values in epsilon sitting here, but there is nothing like we subtract from, right? we subtract from something, but here we don't subtract anything here, and we subtracted something there. So can you bridge the gap here?
So tau is like the function
Right.
that it chooses indices.
Exactly. So so the class of function in this, putting this definition of epsilon biases in context, so you have this function of the form tau comma x, right, for every tau. In 0, 1 to the n, maybe minus 0, the zero function. Right, so these are the functions, good. And who's the PRG? I mean, there is a set here, not a PRG.
The set is the image of the...
Very good. Yes, exactly. The set is the image of the PRG. Right, so here I didn't want to write I didn't want to write a PRG like that, but really if you have a set in 0, 1 to the n, it could be a multiset, but let's consider a set for a second. Then you can always kind of artificially, if you know the set size, artificially you can write it as a function that maps kind of the element name from the set to the set element. Right, so for example, in our case, I told you that there is a set of this size. So I can definitely write, I cook up this function artificially a little bit. Right, so this is log to the base 2 of s and outputting 0, 1 to the s. And I mean, I'm just using this as a name, right? I'm just using this as a name for the element from the set. Right, so if the set is of size 16, I need 4 bits to kind of can encode or give names to the elements in some arbitrary way. And so this set can always be written as the output of a PRG, which simply maps in some canonical but fixed but non-important way these strings with the names of the elements of the sets, with the elements of the sets. Just encode the elements of the set by this in some weird way by strings like that. Maybe you need to have some absolute, some roof or something, but that never mind.
But that's it shouldn't be efficient.
Good. So I didn't talk about efficiency at all so far. I'm going to. You're alluding to the fact that I never said anything about the efficiency of the PRG. That's true. I will talk about it in a minute, really. But you see, I mean, and what's missing? This thing is missing. Just before moving to the point you mentioned, why I'm not comparing the output of the what's going on? Where is this thing? And why there is a -1 here also?
It's just 0. The
Right.
expected...
Exactly. So I mean, it appears here actually, but it's -0, right? Because for any non-zero tau, namely for every function in this family, the expectation is 1/2 before you put the -1, right? Because exactly half of the x's are in the product 0 with tau, and half of them are 1, because tau is non-zero. And when you kind of do this -1 translation, the expectation of -1 so this expectation when you take S to be uniform is 0. So that's the only little thing that happened here. And the -1 is just a little gadget, right? It's nothing more than that. Just easier to, if you are 0, 1 and you want to say I'm close to uniform, when uniform is 1/2, which is annoying, I rather the uniform to be like 0. So I'm just doing a -1 to my bits, which translates them to 1 and -1 instead of 0 and 1. Or 1 and 0. Good, so an epsilon bias set is actually a PRG, and actually even before talking about efficiency, we talked quite a bit about the fact that I want the set to be small, right? I mean, if the set is not small, then I can easily construct a PRG, just take the whole cube, every string in every n-bit string. So the fact that we want a small set is in the larger context of pseudo-random generator still holds. We usually want a PRG that stretches few bits to many bits. I mean, the point is to try to imitate randomness with as few random bits, like truly random bits as possible, benefiting from the fact that we are not trying to output random bits, we are trying to output pseudo-random bits. Right? So for example, for the class of linear tests, so these are linear tests, the set size that we require is where is this thing? Is n over epsilon squared, but in terms of the number of random bits that we need in order to generate an element from the set, that's in our case, which we denoted by R before, if you remember, in the definition, like here, R for randomness, by the way. So R is, the log of that, so it's like, maybe 2 log n over epsilon plus a constant. Right, the log of that is 2 log n over epsilon plus a constant. So it's kind of amazing that you can use only log n, kind of ignore epsilon for a second, log n bits or 2 log n bits, and stretch them to n bits, exponentially many more bits, that looks random, even though they're highly non-random. They look random to any linear tests. Good. So this parameter R is a crucial parameter. I mean, the point is to construct PRGs that have small value of R, and the input for the PRG is called the seed, and so R is denoted as the seed length. Okay, so actually the input, I should say, is the seed, and then therefore R is the seed length. And when we're trying to construct PRGs, and I will say why we care about those, we try to do 2 things. First, kind of information theoretically, we are trying to get the seed length as small as possible. And in what sense? So you want it as small as possible as a function of the class that you're trying to fool and epsilon. Yeah. Usually the dependence in n is coming from the class that you are trying to fool. So you don't have to specify that you also want a dependence on n. I mean, it will come even if you don't want it, because this class of function is function on n bits. And the second thing you want, related to what Itai said, is that you want this PRG to be efficient in some sense that is proper in the context that you're working in. Like usually you want, maybe a time-efficient PRG, but sometimes you don't care about time, you care about space, or to what extent the PRG parallelize, and or whatever. What's the degree of the PRG as a polynomial? Whatever computational aspects that you care about, you can impose conditions on the efficiency of the PRG. And usually it's related to the class C, right? If the class C is, small, functions or languages computed in small space, then you probably want the PRG to be computed in also small, maybe larger, but still small space. If C is the class of AC0 circuits, maybe you want PRG to be also in a circuit class which is low in the hierarchy and so forth. It doesn't matter if you don't know what that is. Right, so when we construct PRGs, so we want 2 things. First is, again, information theoretical. We want short seed. And the second thing we want is explicitness or efficiency. Choose your word, I don't care. Okay. Now,
But there are 2 different considerations, right? What do you mean, choose word?
Sorry, again, I didn't get it.
Like it's 2 different considerations, right? It's not interchangeable.
Right. For example, I can kind of easily do that. We'll do it today if you don't care about explicitness. But usually you do care about explicitness, and then
No, I mean explicitness and efficiency.
Oh, well, I don't know. I mean, I know what you're saying. You're saying, maybe you can. I think I know what you're saying. Do you ask me to being able to evaluate the PRG efficiently, or to give an explicit description of the PRG? That's what you mean?
Even more like it can be explicit, as in I know how it looks, but maybe we don't have very strong lower bounds, but maybe there is a lower bound to say, even though I know the structure of this PRG, we cannot do it in P. Or I don't know.
see. Right. So for example, good point. So for example, maybe the PRG uses a majority gate, and so it's explicit. I know I know it's a majority of some parities or something. It's very explicit, but it may not be efficient when you are talking about AC0 circuits, which cannot compute neither parity nor majority.
Yeah, exactly.
Right. Good. So right. So you are correct. I just kind of meant it like in a slang. I just want it to be okay computational wise in whatever you're doing, and or efficient. Okay, so I mean, this means I want it to be valid in terms of the computational aspects. You can use it. It's valid. It's a good PRG for your own application.
And when you
and by
said
the way-
about the examples of AC0, if C is AC0, maybe we want something low in the hierarchy of the parallelism, blah. Do we know that it cannot be the same? Is it like obvious?
Right. So typically, unless weird cases happens, like it is usually the case that PRG should be stronger than the class it's trying to fool. But it depends. Some low classes are weird, and so I don't want to commit on an answer. But actually, usually you don't even mind. So in pseudo-randomness, we want, for example, we will be very happy with a good PRG for AC0, good in the sense of a short seed, even if it's just in P. So sometimes we are allowing much more computational power for the PRG compared to the class. So it depends only on the context and what we know and what we want to do with it. And sometimes you want it to be as close as you can to the class that you're trying to fool. But it's context dependent. But you should just be aware of the fact that it's a kind of a meta item. There are many computational contexts in which this can be interpreted. But I think even a more subtle question is, where's the input? Like usually when you have a randomized algorithm, there is an input in the input tape, and then there is a randomness sitting in the randomness tape. I mean, don't worry about the space issues and so forth, just in general, like you have the input and you have the actual input that you're trying to do something with, and the randomness is not the issue. The randomness is just the randomness. The input is the kind of the star player, and the randomness try to help you compute the function on the input. And here you see I kind of ignored completely the inputs. So the class of functions, I don't know where they are. Yeah, the class of functions that we are looking at, they are only given as input the randomness, right? You see, because I'm kind of feeding to the function only one input, and I feed it uniform distribution. So probably the person who thought about this definition kind of consider the input to the function as the randomness. And so where's the input? So right, so as Ben said, the input is typically the player, like it's the main player. But when we are trying to do pseudo-randomness or de-randomization and so forth, I'll talk about that in a second. The randomness takes the key role, and the input is just kind of an annoyance. We have to work for every input, so we kind of in a sense fix it. So when I write things like that, when I look in a function from C, what really usually happens is that there is some function or algorithm that has an input. So usually, just to put things in context, in particular in the context of the randomization, so usually you have some algorithm, let's call it A, and it gets two inputs, like an actual input and some random string. Sometimes people even do like a semicolon to make sure that it knows its place. And that's usually, because it's the star input, that usually is an n-bit string. And that's, who cares? I mean, depending on the context, but it's usually bounded by some polyN if the running time is polynomial and so on. But it's some string. I don't care how many bits, say, just for example. But in the context of de-randomization, I mean, the use of pseudorandom generators is typically in de-randomization, almost always. So in that context, what you are actually doing is you actually consider the function f. I don't know why I moved to different color. You consider the function f on input r where you fix x, right? So for every algorithm in your class and for every input x, you generate a function f. F is like a function of a, I mean, it's a function that's determined by a and x, and now it's only a function of the randomness. And that's the function that the discussion about PRG starts from. I care about functions like that, okay? So for example, if you are trying to de-randomize, so if you have this, if you have an algorithm, I don't care exactly if it's space bounded or time bounded or it's whatever, and you want to, but it's random, it's a randomized algorithm, and you want to de-randomize the algorithm and therefore the entire class, in the sense that you want to find another algorithm that has the same functionality, but it's deterministic, then what you can do, I mean, you could always have done the following. You could have iterated over all possible strings, random strings, and it will take you some time probably, because the randomness usually is, I mean, I said that I don't care about how many bits are there, but there are usually plenty of bits there. And you can, but if you have the time and the resources or space or whatever to have that, you can kind of emulate A on every possible random string, collect the results and see what happens. So for example, if you are talking about two-sided algorithms, you will be able to figure out if there are at most 1/3 or say, or at least 2/3 of the random strings that accept this particular X. And therefore you can actually de-randomize the class, this function, and therefore the class. But that's inefficient, completely inefficient, because usually the randomness is heavy, it's long, and so you have to work in exponential time in terms of the random bits. But if you have a PRG, it will allow you to actually reduce the cost of doing that, because instead of going over all random strings, what should you do?
You can use the PRG to use a lot less random strings and then iterate them.
Exactly.
But Gil, there's still something I don't understand. Even if you go to all possible random inputs,
Yeah.
what do you do after that? You iterate everything, you remember all the possible results, and then what you do?
Right, so I go over every random bit. I don't even really have to remember every possible result. I'm just like adding how many accepts I saw, how many ones.
Okay.
And then, say it's like a typical two-sided error. You accept if and only, so if X is in the language, you have at least 2/3 chance of acceptance and otherwise at most 1/3. Then you can just check and see if you got more than 1/3 or less, more than 2/3 or less than 1/3. By just
okay.
counting.
Okay, we're talking about like okay, I get it. Because we can't really output a result that fools the same function we discussed earlier, because we're not outputting anything random.
Right. So you do nothing random. You just iterate it over possible randoms. That's usually the way you prove BPL is in X and so forth, P space, whatever. Because you just go over all possible ways of doing that. And as you said, if we have a PRG and it's first of all efficient, so computing the PRG is not like the bottleneck of the whole thing, because you need to compute it all the time, and its seed length is small, it's a short seed, then the running time will be exponential. Say we're talking about time, it will be exponential in the seed length, not in the randomness required for the PRG. And the typical golden, I mean, ideal thing is that usually it's that the randomness required is logarithmic in the bits you want to output, and therefore being exponential in something which is logarithmic puts you back at polynomial, right? So So that's the context. That's the way pseudorandom generators are useful for de-randomization. Right. Good.
Why BPL and not BPP? All of BPP?
Yeah, of course. That's just my day job. I'm doing space. I'm not in. Yeah, definitely BPL is BPP. I meant the running time is the important thing here. I just don't believe in BP, like analyzing BPP anymore. We know everything that we can. Okay, so let's say an example, okay? So let me give you a concrete example of a complexity class called decision trees. Have you seen this decision trees model ever? Maybe?
In machine learning.
Oh, okay. Right. Maybe, yeah. I hope it's the same. So, good. So a decision tree kind of captures the query complexity of a function. So how many things you have to query in order to figure out what's the output of the function. So let me just give you the model. So you have a function on n bits, right? And the computational model proceeds as follows. It has the structure of a tree, binary tree. It doesn't have to be like complete, or I don't know how they call it. It could look like that, or maybe like that. Every node is indexed by one of your variables. So maybe that's x7, that's x1. You can repeat. You can write x7 again, x5, xn, and so forth. And the leaves are actually not, so the leaves are actually not indexed by variables. So let me fix it like that. The leaves are indexed by the output of the function. So for 0, 1 function, it's like maybe 1, 0, 0, 1, 1, 1. Okay? And the edges are labeled by 0, 1, in the 1 by 0 and y by 1, say. It doesn't really matter, but let's do it like that. You can always kind of flip it. And so you have such a thing, right? So every internal node is indexed by a variable, edges are labeled by 0 and 1, and the output leaves contains the output, and the leaves contain the output of the function. If the function has more or other output values, you can just put them on the leaves. And the computational proceeds as you might expect. You kind of start here, and you look at x. So this computes some function. And let me tell you what the function is. You read x7 because this kind of computational model tells you start by reading x7. And depending on what you read, you are moving either to the left or right, if you read 0 or 1. So say you read 1, and well, the tree now tells you, read x5, query x5, and essentially output x5, right? If you see 0, output 0, if you see 1, output 1. And that's it. I mean, if you read x7, if x7 was 1, and then after 2 queries, you are done. You know the function. If not, you need to read x1, and according to it, the tree tells you whether you should read x1 and or x4 or x7. Actually, this kind of is, you don't really have to do that because everything is 1 here. You could just put a 1 here, but never mind. I mean, whether you put 1 or 7, even if you read x4 or x7. So this kind of computational model, so if your function can be computed in a tree like that, well, every function can be computed by a tree like that. But if a function can be computed by a tree like that, which is like economical, it's like maybe it has low depth or small size, then in particular depth, it means that you don't have to have too many queries to figure out the output of the function, right? For example, one nice example that has low query complexity is the indicator or index function. So this is a function that has n bits, and in the first log n bits, what you do is the following: you read the first log n bits, and you think of it as a pointer to this array, right? It could point to itself, but it will probably point something else. Kind of the address. It's called the address function now. I remember, because it's the address. And then what you see is what you output, right? So what's the depth of a decision tree you need in order to compute this thing?
Log n plus 1.
Log n plus 1, right? Because you need to read log n bits. I mean, I don't want to actually draw the tree, but you can imagine. You need to read these log n bits, and then one more bit in order to know what you're outputting, the bit corresponding to that. And the identity of that bit really depends on those bits, but you can do that with decision trees because the path is exactly what you read. The path, the log n path, will kind of encodes the bit you're trying to read, right? Good, so that's a log n, or maybe 1 plus log n. We will say that the decision tree complexity of this function is log n plus 1. It actually is log n plus 1, not less. I mean, typically, function requires reading all the inputs. Can you think of a very simple function that is like very sensitive to the input, so you need to read everything?
XOR maybe?
Exactly. That's the worst, parity. I mean, there are many worsts, but that's the worst. Parity, you're not sure what's the output until you read the last bit, right? Good, yes, exactly. But on the other hand, I mean, so let's see. So if we draw the decision tree of parity, so you read x1, right? If it's 0, I mean, regardless of what it is, you read x2. Well, I don't want to actually do that now, I see. I thought it would be simpler. Can you give me another function which is easier to draw and still has a high depth decision complexity, tree complexity? Essentially any function that, exactly. And right, until you read the last bit, you don't know, maybe everything was 0 and then the 1 will come at the end for the whole function, right? And that's actually easier to draw, but never mind that. So what I want to do is to tell you the following theorem, which we'll start proving after the break. We'll prepare ourselves for it. So kind of surprisingly, I mean, as you just said, like parity has high decision tree complexity. I mean, it's really sensitive to its input. And epsilon bias sets are like PRGs for parities, right? Linear functions over F2, these are really parities. So nonetheless, even though epsilon bias sets are originally, and by definition, they are pseudo-random generators for parities, and even though parities seems to have kind of nothing to do with decision trees, because as functions by themselves, they have high decision tree complexity, nonetheless, an epsilon bias set is a good PRG for decision trees. So what I'm saying is that any, okay, just by its definition, any epsilon bias set, and you can think of it as a pseudo-random generator, as Yarden told us, this is the image of the pseudo-random generator. So I'll just refer to it as a PRG, even though it's a set, is okay, size of decision tree times epsilon PRG. I'm putting two definitions in parentheses at once here for F. So what I'm saying is that if you take any pseudo-random, any epsilon bias set, it's going to be with some appropriate error. It's not going to be the epsilon that you started with. It's going to be a pseudo-random generator for any function. However, the error that the way it deteriorates is going to multiply it, by something. It's not going to stay epsilon. And the thing is it's going to multiply by is what's called the decision tree complexity of the function, but in terms of size. So this thing is the smallest size decision tree computing F. Size is number of leaves, by the way, or number of nodes. It doesn't really matter, but it's easier to work with leaves. So what I'm saying is that an epsilon bias set, if you have some function, and it is computable, even if you don't know how to do that. If it is computable by a decision tree that doesn't require too many leaves, then the epsilon bias set will just fool it to that extent. Okay? Questions? I mean, that's kind of crazy. It's not, I mean, it's not going to be very hard, but it's not expected initially. Because again, I mean, I don't know, it seems to be unrelated initially. Parity are not good friends of decision trees. Okay, so the way we'll prove this theorem and other theorems, this is just an example, is using Fourier analysis, which of course we'll talk about after the break, but